Okay, welcome to lesson 111 on balancing chemical equations. Now, balancing chemical equations involves the law of conservation of matter, in which we need to understand that atoms are rearranged in an equation, in a chemical reaction. We do not create or destroy atoms. So let's always start with our simplest example. This is one of the most exciting demonstrations to do with kids, where you take two gases, hydrogen and oxygen, and you bring them together and you get a nice explosion and you end up with a little bit of water. So when we write the equation, we have the diatomic gases, the H2 and the O2 showing on the left side of this arrow. The arrow saying that we've yielded something or produced something, and in this case we've produced water. So this is a skeleton reaction though, because if we look very carefully, we can see on the left side two oxygens based on this subscript here versus one oxygen on this side. So we have to balance these. Now we cannot change subscripts. So the first thing we want to do whenever we start working on balancing equations is we want to just circle our molecules so we know not to change anything within those circles. Instead, we change the coefficients or the numbers that sit in front of each of the molecules. So in this case, whenever we work with the synthesis of water, we want to balance by starting with the most complex molecule, in this case water, H2O. And so if we look at the hydrogens, well, they're balanced, but we have two oxygens on the left and we only have one on this side. So we can put a 2 here, and that will give us the two oxygens. But now we have 4 hydrogens rather than 2 on this side. So we put a 2 here, and now we have 4 hydrogens. Now we can make a nice chart in which we list our elements down the side here, and then we just simply do a left and right, so the left side and the right side. And we check, we have 4 hydrogens and 4 hydrogens. We have 2 oxygens, 2 oxygens, so everything is balanced. So we start with the skeleton equation, and then we consider the law of conservation of matter, and we make sure that we change coefficients until we have the same number of atoms on both sides. So let's look at something that confuses students. Lots of students, they would love to have just been able to, when they balance the H2O, they would love to say, well, if it's 2 oxygens here, then I will just put a subscript. Well, I mentioned to you, you circle your molecule and you don't make changes within that circle. So we've got to keep in mind why. Well, water is H2O, whereas hydrogen peroxide is H2O2. So if you added that second subscript, the 2, you have changed substances, and we do not do that when we balance equations. So I just want to clarify that we always change the coefficients in front, and coefficients are the numbers in front of the molecules. All right, so let's look at a more complex equation right away, and that is something like a combustion reaction. And again, we're going to use the ping pong back and forth, back and forth. We're going to start at the most complex, and we can see right away we have 6 carbon atoms on this side, don't we? So we only have 1 on this side. Let's put a 6 here. And when we put a 6, we go, well, we've got the carbons fine. We go over to hydrogens. Well, there are 6 on this side, so let's make 6 here. And it looks pretty good so far. We started with the most complex. We've seemed to have everything going. But now we see an odd number of oxygens here, and we see an even number here. And so we end up with a total odd number, don't we? We end up with 15. Well, we could do 15 halves here, and that would be balanced. Except for we don't do fractions whenever we balance. We go to the smallest whole number. So let's multiply everything by 2, and we can end up with a balanced equation. So we end up with this hydrocarbon, 15 of the diatomic oxygens, and then, of course, 6 waters and 12 carbon dioxides. Now, if we look at these numbers, which we want to get used to looking at, we can see they're important to us, and we can see we start getting a ratio of 2 to 15 to 6 to 12. And that ratio is going to be important to us later on as we're working on stoichiometry problems. So balancing is important that we know to go to the smallest whole numbers. Let's look at the next problem. This is a great reaction because it's a dance that is occurring. You see that aluminum is dancing with the chloride, 3 chlorides actually. Lithium is going to come along and actually is going to kick out aluminum, and it is then going to be dancing with the chloride. So this is called a single replacement reaction, and it's really nice. But this reaction is also nice because it's easy to balance. Right away we see these 3 chlorides, and as soon as we see the 3 chlorides, that means we need to put a 3 on this side. Once we've put the 3 chlorides, we need 3 lithiums. We put 3 lithiums here, and we're done. So this is the fastest kind of reaction to balance. So if you see a single replacement like this, just look for the anions and the subscripts. Then you can quickly figure out what to do. All right, let's look at the next problem, which is using polyatomics. So we have 2 polyatomics here that we need to worry about. We have the phosphate group, which is PO4, and then we have the hydroxide, which is the OH-. So we want to make sure that we keep these together when we are working with them. In previous balancing equations examples, we were looking at elements. Here we want to keep the polyatomics together, and that'll make it easier. And you might say, whoa, wait a second. I don't see hydroxide on this side. Well, you'd be incorrect. There it is. It's hiding. We have this and this together. So there's the hydroxide. And there's a free hydrogen that is going to come over on this side. So when we start balancing, we start with our most complex. And let's start with the calcium phosphate. We see right away we have 2 phosphate groups. Therefore, on this side, we're going to put 2 phosphate groups. We also have 3 calciums. So let's put 3 calciums here. And we can see right away we have the 6 of the hydrogens. And we have we then have 6 of the hydroxides. So to get everything to balance out, we're going to need to put a 6 right here, aren't we? Does that work out? Well, let's see. We have 12 hydrogens on this side, and we have 6 hydrogens here, and we have 3 times 2, 6 here. So we've balanced this out, haven't we? And we have 12 on both sides. All right. So this is probably the most complex would be polyatomics. The trick is keeping the polyatomics together, and then everything will be fine. Hope this helps.